Hey, so this lesson is all about polymorphism, which is the ability of a member function to take on many forms, and based on the type of object that invokes the function at runtime, the function can assume the appropriate form. There are two ways in which function invocations are resolved. We have compile time binding, also referred to as static binding or early binding, and in that case the compiler resolves direct member function invocations at compile time. Direct simply meaning that we are not working with pointers or references. Right, so if you have overloaded member functions and overloaded operators, then the compiler is going to resolve which one is appropriate to invoke at compile time. And typically when something is done at compile time, then that will mean when you actually run your program, it's going to be more performant and it may use less memory. We also have runtime binding, also referred to as dynamic binding or late binding. This is where indirect function invocations, so via pointers and references, are resolved at runtime. This is really the important part of polymorphism because this allows the function to assume the appropriate form, or in other words, the appropriate member function is going to get called, depending on the type of the object as opposed to depending on the type of the pointer or the type of the reference. The virtual keyword is what enables polymorphism. So we have an example at the bottom of the slide. We do the virtual keyword, followed by the type, in this case void, and the function name, so toString, the parentheses, followed by const if you want to qualify the member function as const, and then of course the body. So basically you just prefix everything with the virtual keyword, right? Let's move over to Visual Studio and we'll look at an example of some of the problems that we can run into when we do not use the virtual keyword, and then we'll also look at the benefits of the virtual keyword and polymorphism. I have this simple example in Visual Studio. I have a base class base, with a public member function. It's just a simple toString function which prints out base, the scope resolution operator toString, just so that we can see which version of the function is invoked. Then we have this class derived, which publicly derives from the base class. Then in the public section I override that function, so I have void toString again, and that is going to print out derived toString. Then I have this display function. We'll use that in the next example. In main I construct base, which is of type base, and derived, which is of type derived. Then I do base.toString. Remember, those are public functions, so I can do derived.toString as well, and I simply have this end of program string as well. If I build and run this, we can see that the base toString function is invoked in that first statement, so in the toString function call on the base object, and we also get the derived toString function call on that derived object. But what if we have a pointer or a reference? I'll just comment these two lines out. Alright, so I have this base pointer, which is a pointer to a type of base. We allocate a new object on the heap, new base, and then we do base pointer toString. Of course, later on you want to clean that up again, so you want to deallocate whatever base pointer is pointing at. I'll build and run this, and we get base toString printed out. Now you may get some warnings because we are not actually using this anymore, these two variables, so I'll just comment those out. Now what we can do in C++, because a derived is a base, right, a derived is a base because it publicly derived from base, what we can do is we can allocate an object of type derived on the heap. So we do new derived, it will return that address and assign it to the pointer called base pointer, which is a pointer to a type of base. Now this statement is perfectly fine in C++ because, again, a derived is a base based on that inheritance hierarchy, right, as we studied in the previous lesson, and so for that reason we can assign that address to a pointer to a base. Now what would you expect if you do base pointer toString? We can build and run, and it will actually invoke the toString function as it is defined in the base class, and not the one defined in the derived class as we may expect. In this example, we may expect the derived version of the toString function to get invoked, as defined in the derived class. But as I just demonstrated, we actually get the version of the function that is defined in the base class, and that is because we have static binding right here. So this is going to be resolved at compile time, and a similar thing will happen with references. So I have this void display, this global function which has a parameter, a reference to a base, and then we do that base parameter dot toString. Right, we'll be using those objects again, so instead of doing toString over here, what we'll do is, and I'll just comment that out. Okay, so I'm calling this function twice now, this display function. The first time I pass in an object base, and the second time I pass in this derived object. Remember again, we pass by reference to a type of base, even though in the second statement we pass in an object of type derived. If I build and run this, we actually get base toString printed out, so the toString function as defined in the base class, we get that twice. You may expect derived toString in the second line, but we get base toString instead. Again, it's perfectly legal in C++ for us to pass in a type of derived when the parameter is a reference to a base, because a derived is a base. So the problem is not with these statements and these function calls, and it's also not with the parameter. It really has to do with the fact that we have static binding or compile time binding. And so what's going to happen is when you use a reference or pointer, it's going to look at the type. So it's a reference to a type of base, and for that reason it's going to use the base class version of that function. Or in other words, the function as defined in the base class. And the same here, we have a pointer. I'll just uncomment that again. We have a pointer to a base, even though on the heap we have an object of type derived. This pointer is a pointer to a base, and so when we invoke that function right here in this statement, it will again invoke the function as defined in the base class, as opposed to in the derived class, as we may expect. I'll just scroll up here. So let's enable polymorphism by using the virtual keyword. And this is what it'll look like. You have the virtual keyword, followed by the return type of the member function, so void or int or whatever you have. In this case we have void, and then of course followed by the rest. We have toString and we have const, because this is not going to modify the object, and then we simply do the console output again. In derived we also have the virtual keyword, so we basically override the function in the derived class. We don't have an overloaded function, we have an overridden function. Typically with a virtual keyword, you refer to it as we override the function. If it's a non-virtual member function, then typically we simply refer to it as being redefined in the derived class. Okay, so we override the function now, and it's a virtual function. So in other words, we have enabled polymorphism now. Back in main, I'll just comment these lines out again. So I have a base object and a derived object, and I pass those into this display function. Control F5 to build and run. In the first line we get the toString function as defined in the base class, and in the second line we get the toString function as defined in the derived class, right, the function that we override in the derived class. And that is basically what you would expect from this sort of statement and this sort of function invocation, where you pass in the derived. I'll just go and comment those lines out, and I'll uncomment that. I'll be using delete here to delete the base pointer, but we'll also have to talk about virtual destructors in upcoming videos. Okay, so in this statement we have a pointer to a base again, but on the heap we actually have an object of type derived, and then we do base pointer, the arrow operator, toString. If I build and run now, we get what we would expect. We get the toString function as defined in the derived class. And that is thanks to polymorphism and runtime binding. Okay, polymorphism again allows us to call the appropriate function based on the object. In this case, the object is derived. Even though the pointer is of type base, the object is actually of type derived. So we're calling the appropriate function based on the type of the object as opposed to the type of the reference or the pointer. I have another quick example for you. I have the base class and the derived class as we had it before. So the toString functions are virtual. And then I change the main function, so I have two pointers now. I have base pointer, which is a pointer to base, and that is going to point to a base object on the heap. And then I also have base pointer 2, which is also a pointer to a base type, but that is going to point to a derived object on the heap. And then I have an array. Now I have to look closely at the definition of this array. This is an array called pointer array, and this is an array of pointers to type of base. And what does that mean? Well, that means we can add pointers to a type of base in here. So you can see that I've added this base pointer 1 and base pointer 2 in this array. So I have these 4 elements, And I just repeated those, so I have base pointer 2, and then I do base pointer and base pointer 2 again. So don't get this confused with a regular array. This is an array of pointers to type of base. And we've already defined what those pointers point at right over here at these first two statements. In the for loop, what I'm going to do is I set I equal to 0, and then as long as I is less than 4, go and do this right here. So I do pointer array I for the index in the subscript operator, and because this is going to return a pointer, I use the arrow operator, and then I do toString, and of course down here I'll just go and delete or deallocate what base pointer and base pointer 2 are pointing at. Let's just build and run this to see what we get. In the first line we get the toString function as defined in the base class. In the second line we get the toString function as defined in the derived class, and we repeat that again. So we get toString as defined in base, and then toString again as defined in the derived. Because base pointer 1 points to a type of base, and base pointer 2 points to a type of derived on the heap. So that works great, but what happens if I remove the virtual keywords just for demonstration purposes here, and I build and run again? In each instance we get the toString function as defined in the base class, and that's not very handy, it's not very flexible. I'll undo that. This allows us as programmers to think more generally and program in an abstract way, as opposed to being overly concerned with will the appropriate member functions get invoked. That is in the case when we use pointers and references. Of course, this is a simple example. You can have many classes that derive from some base class. So you can assign an object of a type of one of the derived classes, right? You can assign that address to a pointer of the base type. Then you can add a bunch of those pointers in an array of pointers to the base type. And when you iterate through that array and call member functions on that array, again, you as the programmer don't have to do all sorts of checks. It's going to resolve that at runtime, and the appropriate member functions will get invoked. We will continue this discussion in the next video, where we'll talk about object slicing.